Hello people, welcome to 12th standard. Now you're just 1 year older than what you were yesterday, so it's a big change in 1 year. Right, now we are going to start with the 12th standard physics. I've been excited about this since a long time because I really love the course, the syllabus of this 12th standard physics, because it allows you to study about all these interesting things that we are seeing around us. Okay, so well, here I have a list of the chapters for you. Okay, the first chapter is electric charges and fields, wherein we are going to study about electric charges. You know, the charges are at the very heart of the modern technology that we see around us everywhere. Your phones, your computers, washing machines, TVs, refrigerators, everything. Okay, so electric charges, they're really very important. I can't just tell you how important they are. Okay, the second chapter is about electric potentials and capacitance. Well, I'm sure you have heard of the word voltage and you keep hearing it every now and then, right? So electric potential and voltage are very closely linked with each other. So electric potential is what ultimately leads us to talk about voltages. Capacitance, well, capacitor is one of the devices that is used in many modern inventions, or whether that's a phone, a radio, a microwave oven. There are so many. So capacitors are what, again, like one of the basic things, one of the basic requirements of modern technology. The third one, current, electricity, I don't think I need to explain anything about that to you. I'm sure you all realize how important current and current electricity is for us. Now chapter number 4 is about charges and their relation with magnetism. I'm sure you know what a magnet is, but I don't think you ever thought that a charge could have some relation with a magnet. Well, the fact is there's a very close link. Okay, we are going to discover all that in the chapter 4. Chapter 5, we are going to continue with magnets. We are going to see what makes permanent magnets, right? Why is it that some objects, some materials can be attracted by magnets while others cannot be? What are these specific properties that make magnets a magnet? Okay, the next one, chapter 6, electromagnetic induction. That's about a phenomena in nature where by using a magnet we can produce current, right? Yes, you heard it correct. Using a magnet we can produce a current. So this phenomena is used in modern devices like the motor and the generator. So these things are closely linked. Again, current and magnets, well, they're so close to each other, right? Okay, and the last two chapters, 7 and 8, for this part, the part 1, okay, the last two chapters, these chapters are about using these phenomena, these properties that we study in the previous 6. Alternating current is what we get in our houses, right? And whether you believe it or not, but generating alternating current at the power station, I'm sure there are many power stations around us. So generating the alternating current at the power station uses the knowledge of all of these chapters, right? So these are like the very basic ones. Okay, chapter 8, electromagnetic waves. I'm sure you called your friend this morning on your cell phone. Also, that only happened because there were waves coming out of your cell phone, going to the tower, going to your friend's phone, and then getting back to you. So you heard each other talk, you heard each other say things. So you could realize how important electromagnetic waves are given the present situation. Okay, now as you may have noted, here we are using the word electromagnets, everything again and again. So that's because this whole part of the syllabus, the part 1, the first textbook out of the two, this whole thing belongs to the branch of physics called electromagnetism, or sometimes also referred as electrodynamics. So this is where we study about charges, electric fields, magnets, and their behavior, currents, and like I said, how everything is related with each other. So this is a huge portion. It's half of your syllabus of 12th standard, right? But I'm sure you are also interested because this half of your syllabus is related, is the backbone of so many things that you are seeing around yourselves. Okay, so this year actually gives you the opportunity to answer many questions that you may have had since you have started understanding a few things, right? So this is going to quench your thirst for curiosity so much. This year, this physics, you're going to find it relatable. It's all around you. In 11th standard, we have studied about pretty old things like Newton's laws of motion, the law of gravitation, Kepler's laws, like way old, century, about the 17th century. But now, what we are going to study over here, it's a bit recent. And as we progress through these chapters, we are going to be knocking the doors of the 20th century. So trust me, as we get along, you're going to get more and more modern. Obviously, the second part, the part 2 of your syllabus of 12th standard, includes a section of modern physics, right? That's where you're going to study about even more interesting things, but I'll list the chapters when we start the part 2, right? Again, you may have had very curious, very interesting questions like, what is lightning, or what really happens in the clouds that causes a lightning to hit the earth, okay? Or you may have had questions like, what happens when you turn a switch on or off, right? What is really going on? How does the fan, how does the AC, how does the tube light turn on, right, when you just press a switch, right? Or you may have had questions like, well, how does a magnet work? Right? What makes a magnet a magnet? Why is it like magnet can't be made of wood? Right? Or why is it that magnet cannot attract wood? Right? Or you may have noticed that when you rub a magnet on an iron bar, the iron bar itself becomes a magnet. Well, that's very interesting. So from one magnet you could produce one more. Okay. Right? So you may have noted these things. You may have noted that there are some huge cranes that are used in construction of tall buildings, right? So these also they work on these magnets, and that's like a magical one. At the flick of a switch, you turn it on, you turn it off, you turn it on, you turn it off, right? So you have magnets like this which you can turn on and off in instant just by pressing a switch, right? So you see, these are very interesting things. Later on, we're going to answer questions about how atoms are formed and what is inside an atom. I'm sure you have studied in your chemistry classes that proton, neutrons, electrons, all right, but what are these electrons doing, right? Are they sitting over there? Are they waiting for you? What are they doing, right? So, and then we are going to answer the ultimate question. Your body, my body, there are so many things around us, they are made up of different elements. Where did the elements come from? Big question, don't you think? Where did the elements come from? There might be questions like, well, sun is a star, all right, so why is it emitting so much energy? Why is the sun emitting so much light? Why is it so hot? Well, it's April, it's very hot. Why is it so hot? Obviously because of the sun. But then what's the sun doing that makes it so hot that we feel the heat here on earth as well, right? Okay, so there are so many interesting questions that you have the opportunity to answer in this year's syllabus. Okay, So we're going to get started with the first part, right? We're going to get started with electromagnetism, right, which forms a major portion of the physics that we have so far. Okay, so all right, so that's it for the introduction. The next time we get started with chapter number 1, electric charges and fields. Oh, excuse me. Before we get started with all that, I have to tell you about a few instructions. I have to clarify a few points. See, I know you all are locked down at your home. You shouldn't be going out. I hope you are not going out. But the fact is, although it's online learning, it cannot replace the pen and paper. So when you sit with your phone, with your laptop, with your device watching this video, I want you to sit with a pen, paper and your textbook, right? Please don't sit with your phone only and say I'm studying. No, that doesn't work. I want you to sit with all the conventional classroom tools, pen, paper, pencil, etc., whatever you need, textbooks, rulers, draw diagrams, try to read questions as I explain them, refer the book once in a while, while I explain things on the board here. So please don't forget that simply sitting with a phone won't work. Okay, you need your textbook, you need your notebook, you need these things. All right, so let's get started now. Hello there. We are ready to start with the first chapter, the electric fields and charges. Now, the base of this chapter is the charges. So, what is a charge, first of all? What's a charge? Well, charge is one of the very basic, very intrinsic properties. It's a very basic or very intrinsic property of matter, right? It's a property of matter, remember. So, when I say it's a property of matter, that brings up interesting results. It means that matter can have a charge. It means vacuum cannot have charge because vacuum is not matter. It means energy cannot have a charge, again because energy and matter are two different entities. So first thing to remember is that charge is an intrinsic property of matter, and because it's intrinsic, it's actually very difficult to define what charge is. Just like it's very difficult to define what is mass or what is time. Okay, so that's the basic idea about charge. Charge is a property of matter that's very difficult to define, right? And by series of experiments we have figured out that charge is of two kinds, and only two kinds, not more, not less. So these two kinds, they are called polarity. So charge is of two kinds of the charge is of two kinds, or it has two different polarities. So these two polarities are either positive or negative polarity. I'm sure you have heard things like electron is negative, proton is positive. So when we say that a proton is positive, what it means is it has one kind of polarity which is called positive polarity, but the electron on the other hand has the other kind of polarity which is the negative polarity. Alright, so remember, two kinds of polarity and only two, not more, right? It's not like there are three kinds of charges, there are only two kinds of charges. Yes, there's something to remember about absence of charge. You may have heard the word neutral. You would have maybe read it in your chemistry books that proton is positive, electrons are negative, and neutrons are neutral. So when we say neutrons are neutral, what does that mean? Neutral refers to absence of charge. Again, there is no third kind. Number 1, number 2, that's it. An absence of charge is called neutral. Okay, so anything that has no charge is neutral. Now you might think neutral seems pretty weird, but the neutral thing is actually a very common one. An atom as a whole is neutral. Your body as a whole is mostly neutral. This pen is mostly neutral. So that's something which you should understand, right? Under normal circumstances, objects that we see around ourselves, they're all neutral, right? Only under strange circumstances, or only while some chemical reactions are going on or some exotic physics phenomena is going on, we see that objects are either positive or negative, right? I'm sure you know about ions, right? Cations and anions. So cations are positive and anions are negative. So that's because of some phenomena going on, right? We're going to see what that is in a moment. Okay, so like I said, things are mostly neutral. Okay, but then there are some kinds of things that are positive, some other that are negative. For example, cations are positive, anions are negative. So how do we decide whether things are positive or negative? Well, the answer is pretty strange. It's that nature has not decided positive or negative for us. It's we who have just arbitrarily said that okay, this type is now called positive and that type shall be called negative. Well, that's very strange, right? It's like you're saying that now henceforth this thing is now going to be called apple and that one is now going to be called orange. Well, but let's see the history behind it. It was that originally when people knew that if you take a glass rod and rub it with silk, okay, let's say we take a glass rod and take a silk cloth, okay, put it, rub it, so we see that both of them acquire or get some kind of charge. Like I said, objects are mostly neutral, but sometimes when you do some kind of process or phenomena on them, they get charged. So when we take a glass rod and a silk cloth and rub the cloth on the glass rod, we notice that both of them get charged, right? Both of them get charged. And people, especially Benjamin Franklin, the famous scientist, he gave the idea that we should call this one positive and we should call the other one negative. So what do I mean? I mean that Benjamin Franklin decided, or just arbitrarily on his own, based on his own will, chose that when we rub these two objects together, the charge type, the charge kind that is acquired or obtained by glass rod shall be called positive, and the charge type acquired or obtained by the silk cloth shall be called negative. See, it's completely arbitrary. He could have said that this is negative and that is positive, and suddenly we'll see that a proton is negative and electron is positive, but that would not change physics. That doesn't change anything in nature. So excuse me, let me tell you that these two, they're positive and negative, they have been decided by humans, by Franklin. Okay, so when we rub silk cloth with a glass rod, the charge obtained by this glass rod is called positive charge, and the charge obtained by the silk cloth is called negative charge. Okay, right? So this is convention. Remember, nature has not made positive negative, it's we who have given this name, this idea. Well, actually nature has only made two kinds of charges, that's it. Now whether you call those charges red and blue, or whether you call them apples and oranges, well, that's up to humans. But we have found that this positive negative is actually a very good way of talking about charges, right? Why not call them red and blue? Like we could have said that the charge acquired by the glass rod will be called red, and the charge acquired by the silk cloth will be called blue. Okay, so what kind of charge does anion have? Blue charge. And what kind of charge does cation have? Red charge. Okay, so we could have said that, but we are not calling it red and blue. We are calling it positive and negative. That really helps in many situations, right? When we note down some more properties of charges, at that time I'll come back to this point, why positive and negative, why not red and blue. Okay, so keep all this in mind, right? Two kinds of charges, two polarities. One is called positive polarity or positive charge, the other is called negative polarity or negative charge. Now we are going to talk about two things that you obviously know. I'm sure you know, okay, but yet I'm going to write it on the board. You would have heard phrases like this: like poles, unlike poles. Okay, for example, a magnet, north and north will repel. We say that like poles repel, correct? Because both of them are same kind of poles, right? Similarly, in charges, we have that two charges apply force on each other, just like north pole and north pole apply force on each other, they repel. Similarly, two charges, if they are like, that is if both are positive or both are negative, right? So if there are two like charges, that is charges of the same kind, the two like charges, they repel. On the other hand, if there are unlike charges, that is charges with different polarity, let's say north with south in a magnet attracts, correct? North pole, south pole attract, so that's unlike. Same thing here, let's say one charge is positive and the other charge is negative, then these two, they are going to attract each other, that is unlike charges attract. This is pretty much the same as what we have for poles of a magnet, correct? North and north repel, south and south repel, north and south attract. Same thing here, positive repel because they are like, negative also repel because they are like, but positive and negative will attract each other, right? So remember these sentences: like charges repel and unlike charges attract. Okay, now these sentences have actually formed a way of knowing for us that there are only two kinds of charges, there is no third, right? These two sentences have allowed us to prove or discover the idea that there are only two kinds of charges existing in nature, there is no third kind of charge. Okay, so what are these experiments? How do we come to know that there are only two kinds of charges? That's what I'm going to demonstrate now by showing it to you with the help of maybe a ruler and balloon. I'll get whatever I can at my home, okay, but hopefully I'll be able to bring the demonstration to you, get to demonstrate with the best possible tools. So I'll be back over here in a moment, right, with these tools. Okay, hello there. Now we are ready with the demonstration. What I've got is two inflated balloons, they're stunt balloons, and this is just a plastic ruler. What I'm going to do is I'll rub the plastic ruler onto these balloons one by one. So they're going to get charged, the balloons will get charged, and then we are going to see, because both of these are rubber balloons, okay, and this is plastic, when they are rubbed, both of them will get the same polarity charge. That is, when they get charged by rubbing, both the balloons, red and yellow, will have the same kind of charge. That is, they will be like charges. Okay, so these two are like charges, and we'll see what happens when we bring them close to each other. Okay, so let's start. So first of all, I'm going to rub the surface of the red balloon all throughout, very nice, so that there is no portion of it that is uncharged and we can easily see its behavior. Okay. You can do it at home definitely. Just get two balloons, take a ruler, start rubbing it. Okay, be careful you don't burst it because it's possible sometimes due to friction you're going to tear the surface apart. I'm going to put this over here, and now I'll take the other one. Oops. I'll take the other one here. Okay, so I'm doing the same to the yellow balloon now. It's important to tie these threads because we want to see how they move, right? Okay, I think we're ready now. Right, so now let me put the ruler aside. I'm going to grab these two balloons by the thread. Okay, keeping approximately the same length, and you see they're attracting their own threads. But if they're brought close, see they don't quite hit each other, right? If I hold this one in my hand and try to push this away, see what happens. See, it doesn't want to touch it, right? There's some force between them that makes this yellow balloon go away. If I try to bring this red balloon towards the yellow balloon gently, obviously you're going to try and do it like this, they will hit, there's no doubt about it, because the charge on these two is pretty small and the force is still quite less, but I'm sure you do notice that there is some force, there is some repulsion occurring between the red and the yellow balloon, right? Okay. So this is only going to happen if the charges on both of these are like. And I'm sure you realize they are like because we did the same procedure to both of these, and now you will start to see the effect more because I'm gradually making it behave like a pendulum. You see, every time the red balloon comes close, it just pushes the yellow one away, right? So this is happening because both these balloons have the same polarity of charge, that is, they are like charges. So what has happened is that when the ruler gets rubbed with the rubber, the balloon which is made of rubber, what happens is that both of them, the ruler and the rubber, get charged. But let's say that the rubber gets positively charged, the ruler gets negatively charged. So what will happen is both these rubber balloons are now positive charges, so they are going to repel, but this rubber balloon will be attracted by the ruler because the ruler will then be negative, right? But let me warn you, attraction is not a test of whether the objects are charged, right? Because a charged object can attract a neutral object. Yes, you heard that right. A charged object can attract a neutral object, but repulsion is a test of charge. That is, these two objects cannot repel each other until both of them have the same charge, right? So if these two balloons are repelling each other, then the evidence is quite clear that both of these must have the same kind of charge, that is, they are like charges, right? Let me also show it to you what happens if we take the red balloon with the ruler. If you do it at home, be careful, you use the end which you rubbed against the balloon. You can clearly see the ruler is attracting the balloon. Okay, excuse the wind, there's a bit of wind blowing, but Yeah, you can see it here. If I bring this over here, if I bring this over here or over here, you can see the balloon wants to come to the ruler. Well, that is because this end of the ruler will be negatively charged and the surface of this balloon is positively charged. But like I have said, it is also possible that objects can attract neutral objects. For example, this balloon is charged but my body is neutral. You're going to see what happens when I bring it close to my body. It's going to stick to my body. See? Right? It's not going away. It is getting stuck. It is getting attracted to my body or even my hand. Have a look. Okay, I'm sure you have noticed this, right? But like I said, repulsion is a true test. If objects repel, that definitely means both of them are having the same kind of charge. Alright, so now what we are going to do is, in the same demonstration, I am going to show you a device which is used to detect and sometimes also measure whether an object is charged or not. Okay, so let me show you that device. Okay, so what we have here is the electroscope. Obviously, this is a very cheap version of an actual electroscope, right? Now, what an electroscope has is, here there is a kind of a platform wherein you can bring an object close to this platform or even put on it, right, depending on the type, and then that charge will flow through this metal wire. It's a conductor, right? And over here you have got two leaves, two thin metal leaves. Ideally these two should be made up of gold, so such an electroscope would be called gold leaf electroscope, but obviously that's too costly over here. So this is, in the cheap version, what I'm using is aluminium foil. Alright, you could use any aluminium foil if you want to make it at your home. This is just a standard wire, right, that I've got. It was lying waste in my house. This is a typical plastic water bottle and that's all, right? So I've just made a hole through it, let the wire pass through it, turned it and made it like a hook, and I've pierced two holes in those foil leaves, and then they're just hanging over there. So what you're going to see is, when we bring something that has a charge near this, right, the leaves will get that charge. Right, the leaves will take some of the charge and then the leaves will repel each other. So that is, you see, right now the leaves are close to one another, but if I bring something that has a charge on it, the leaves are going to go away from each other. Okay. Right, let me just charge this balloon up again and we are going to see it carefully. Or even better, you could rub it with your hair. Make sure they are not oily, otherwise this won't work. Okay. And have a look. So when I bring this close to the balloon, you can clearly see that these leaves, they're far apart, right? And ta-da! Because actually the charge is not going, because there is no contact, right? See, you can make charge flow from one object to another by contact. And there's also another method which is called charging by induction, which is without contact. So that's what I'm going to show you now, right? But first, before I actually get on with showing you charging by induction, what I'm going to do is I'll describe the method on the board, right? And then we'll continue with this demonstration. Alright. Okay, so the first method for charging is charging by friction. I'm sure you have noticed that when two objects rub against each other, they get charged up. I wrote one example on the board before a while, that is when a glass rod is rubbed with a silk cloth, the glass rod acquires a positive charge and the silk cloth acquires a negative charge. That's one of many examples. I'm sure you have also noted that in winter, especially when your body rubs against your clothes, you see that there is static electricity going on and you would feel a small shock, right? You can get shock over there. So that's because of the charges acquired by your body and by the clothes, right? Okay, so charging by friction or by rubbing is also called triboelectricity. Now this was known since a long time. I'm sure you realize that it's a very simple method. People knew it for what, maybe 2 millennia, right? So there's not much to talk about here except for one thing. See, this gave us the basic the basic ideas about charge, as in when there are two like charges, they repel. How did we come to know that? Well, the demonstration that I did with the two rubber balloons. So when they were put, or they were rubbed with identical identical ruler or with my hair, we realized that both of them would have the same charge, correct? The red balloon and the yellow balloon. So now if they have the same charge and when they come close to each other, they are repelling each other. So that gives us the sentence that like charges will repel each other. So, and then finally people also figured out that if you take it with the other kind of charge, right, so positive with negative or negative with positive, they attract each other. So all this has played a very important role in the basic understanding of how charges behave, right? Now what we are going to do is we are going to take a modern view of this one, right? See, back in the 18th century people didn't know a lot about the structure of objects or the atoms or anything, but now we do know. So for example, let's say that we have the glass rod, okay, and we are to rub it with the silk cloth, right? So when we do that, when we rub them together, what happens is we say that this gets a positive charge. Remember, that charge is called positive, okay, and the charge that we get by rubbing them, okay, on the silk cloth, that charge is called negative. So when we rub them, this one positive, that one becomes negative. So what is really happening, and we know that now, is that the electrons, some of the electrons that are present inside this glass rod, obviously every object is made up of many atoms. So these atoms will have lots of electrons. Some of those electrons, they go to the silk cloth, obviously when they are in contact, right? That's what I mean. When you are rubbing these two against each other, that is when the transfer that occurs. So some electrons are transferred from the glass rod to the silk cloth. Now I'm sure you have studied this in chemistry. You realize that if electrons will leave the glass rod and go to the silk cloth, this will obviously become negative because electrons themselves are negative, right? And the glass rod from which the electrons have left would become positive. All right, okay, so this is the modern understanding of how objects get charged when they are rubbed against each other. So basically it's a transfer, it's it's a motion, it's a movement of electrons going from one object into the other object. So whichever object loses electrons becomes positively charged. Let me write that here. So this glass rod loses electrons, not all of them, right? Remember that not all electrons go away, that would be disastrous. Some electrons, okay, and this one gains those electrons, right? So the one that gains electrons, okay, the object that gains electrons, that gets the electrons from the other one, will become negative. So this is pretty much the same as you have studied in chemistry. A neutral atom, if it gives an electron away, it becomes a cation, a positive ion, and if it gains an electron, a neutral atom, when it gains an electron, it becomes an ion. Okay, so that's what we have, right? So this is a very basic thing here. There's no complication. Objects just get rubbed and charges transfer, right? So that's how we have it. Okay, now we are going over to the second one, the second method of charging objects, that is charging not by friction but by induction. Okay, so that's what we are doing now, right? Well, the second method, charging by induction, well, this is a method that obviously works without contact, right? That is, the two objects involved in this method, they don't touch, right? But this method is slightly different from the triboelectricity method, because in triboelectricity method, or by rubbing, what you can do is you can take two neutral bodies and get both of them charged, right, without the help of any other charge, right? Okay, so like when we say we take a glass rod, we take silk cloth, when they are separate, there is no charge on either of them, so this both are neutral, but then when you rub them against each other, they both get charged, right? But charging by induction is slightly different. A basic requirement for charging by induction is that you need to have some charged body, right? You need to have at least one body that is already charged, because you are going to use it to charge other bodies, right? So let's see the steps. So step number 1. Step 1 is we take that object which is having a charge already. So let's say that we have a rod, glass rod, let's say, which is rubbed with silk cloth, and now it is positive. So I take this glass rod, okay, which is already positive. Now I will bring it close to two metal spheres which are kept in contact, right? So what we want to do is we want to charge these two metal spheres, right? That's our goal. Okay, by using induction we want to charge this. So let's see how everything works. So we take this the glass rod. We take the glass rod and we are going to bring it close to the metal spheres which are kept in contact. But what we have is that here there are insulating strands. These strands are insulating. Now that means charges cannot flow through this. Okay, insulator is something that does not allow charge to flow. Remember, metals are conductors which allow charges to flow very easily. Okay, and insulators like wood or plastic, they are those objects, those materials that do not allow the charge to flow through them easily. Okay, bad conductors or insulators. Okay, so that's the situation. So like I said, this is what we start with: one glass rod which is already charged, let's say positive, and two metal spheres. And let me just mark that out as well. So these two are metal spheres that are in contact. Okay, now what we do is, like I said, we get the glass rod close to them. First, let's say it was far. Now we get the glass rod close to them, but yet not touching them. Don't forget, it's not supposed to touch. So when we do that, because metals allow charges to flow easily, what will happen is that the positive charge of the glass rod will start attracting the electrons from the metal sphere, right? Because obviously metals are made up of atoms. Atoms have so many electrons, and I'm sure you remember that metals have free electrons. You would have studied that in 10th standard, that metals have many free electrons which are easy, which are very easy to move. They can move around a bit in the metal. So when we bring this close, the electrons, some of the electrons, not all, some of the electrons will start moving towards the left side, and they will settle on the leftmost surface. Remember, they can't jump, right? Air is an insulator. Charges don't flow through air just like that. I mean, they can, but it's very, very tough, right? We'll talk about that later, so don't worry too much about it. So what happens is, at the same time, what happens is, because the electrons will move towards the left side, okay, so those atoms from which the electrons leave, from which they are removed, those atoms become cations or positively charged. What do I mean? Let me just show that in a bit more detail here. Let's say there was one atom over here, but the electron from that atom got attracted towards the left side, and now it has moved, right? Now it has moved. So now this atom has lost its electron, right? the atom has lost its electron. So now the atom on the rightmost side has now become a positive ion, a cation. Okay, right? So that's what is going on over here. So basically electrons start getting attracted, they settle on the leftmost edge, and the positive charges, they are on the rightmost edge. Now we're going to play the evil trick, right? You can see over here in these two metal spheres, what we have is the negative charges, okay, are on the left sphere, and the positive charges are on the right sphere, and these stands are insulating. So the only way they can go back is through this contact. So we will use our evil mind, okay, and we will separate these two spheres, but we will not remove this. Okay, we'll keep the glass rod right there, and we'll just separate these two and break that contact. So this is what it would look like. So we have, okay, the sphere 1 and now the sphere 2, but there is no contact between them. The contact is broken, but the glass rod is still there. Okay, let me just draw this very clearly so that each one of you can see it in the video like this. Yeah. So what we have is this. Now we have separated these two. Now you might ask, how can we separate them? Again, like I've said, that's what these stands are for. You put your fingers between these two and then let them move, let them slide. Okay, so now what we have is that this glass rod is positively charged, and now the negative charges, they have gathered over here. Okay, the anions have gathered over here, you could say so, and the cations have gathered over there, right? So that means these two spheres, sphere 1 and 2, again let me just put labels everywhere, spheres 1 and 2, right? So sphere 1 is now having a net negative charge, and sphere 2 is now having a net positive charge. So what I'll do now is I'll just remove this rod. So the fourth step is remove the rod, and now what you have is, let's say these two are quite far, okay, so what we have is now that this sphere number 1 is negatively charged, and then there is a sphere number 2 which is positively charged. So you can see that at no point in this whole method did the rod touch any of these spheres, correct? That's why I'm saying that charging by induction is without contact, right? That's why I'm saying that charging by induction works without contact. This rod doesn't have to touch anything, and yet these objects will get charged. Now let's say I want the negative charge, I'll simply discard this one. Okay, I don't want it. Or let's say I want the positive charge, I'll discard the negative one. It's fine really. Okay, so what this means is, what this means is you don't need this rod to touch anything, right? There's a way in which I like to describe it. See, this is like showing a little kid a lollipop and luring the kid, or forcing the kid to come towards you because of the desire to have the lollipop. You can see you're showing a positive charge. Okay, so okay, electrons, come here, I'm going to give you positive charge. Okay, now once everything is in place, the evil mind starts to work, and we execute our plan, and the electrons are separated from their family. Alright, so now the electrons can't go back, right, because the bridge is broken. Okay, so what this means is, we show them the lollipop, we show them the positive charge. Okay, come here, I'm going to give it to you. But then once our job is done in figure number 3, we'll say, right, what positive charge, what lollipop are you talking about? I got no lollipop. Okay, so there's nothing, right? So we don't really have to sacrifice our positive charge, and yet the job gets done. Okay, so this is the method of charging by induction. I really hope that you'll be able to write the steps on your own. Okay, every diagram has a story behind it, has a description behind it, right? Two metal spheres in contact having insulated strands. Here we have got a positively charged rod, right? We are going to bring it close to it. So some of the electrons from these spheres will move towards the left side. So the left surface will gather or will develop a negative charge, but the right surface will develop a positive charge, and then we break the contact, but we don't remove this yet. Okay, the key thing is this contact should break first, only then this rod should go away. For example, if I would have taken away the rod, what would happen? Okay, I want you to think about that. If we take this rod away in this situation, what would happen? Right? It's very simple. Think about it carefully. Think about charges, positive, negative. What would they do? Right? So now what we have is, in the third step, we have the charges separated. We just remove the rod, and that's it. We are done. We have the two negative and the positive charged spheres. All right. So that's all about charging by induction. Okay, now there is another method to charge by induction. This method is given in your textbook, but there is one more method, right? So that's what we're going to start with now. Well, the alternate method to charge objects by induction is what we're going to talk about now. Another method. Remember, the basic idea is the same, that you don't have to touch the object, right, that you want to charge. Okay, so before we get started with that, there's just one word that I have to explain to you, and that word, it's an important word, not just for this topic. It's usual follow in many more topics now. The word is earthing or ground. Whenever you see earthing or ground, what this means is, the object that we say is earthed or grounded, it is connected with the earth. So what do I mean? So let's say someone says there is a sphere, right? Someone says there is a sphere, and then says that the sphere is grounded. So the symbol for grounding or earthing is this kind of sign. Okay, it's like Wi-Fi, if you could remember that. Okay, so when we connect it like that, that means it's connected to the ground, it's earthing. I'm sure you have heard that, people talking about earthing in your house, right? So what does that mean? What that means is that this object is now connected directly to the earth, to the ground. Now, why so? What does that do? What purpose does earthing serve? Well, the purpose is that the earth actually is a big, or rather very large, store, right? Store as in something that can hold, okay, it can store charge, right? So earth is a big or large store of charge, right? So what happens is, it can easily give or take charges from other objects. Okay, so what do I mean by that? So let's say this metal sphere was having some charge. Okay, when we connect it with the ground, the earth can easily take up the charges, right? The earth can easily take up the charges. That is what will happen is, suppose this was positive, so electrons will start flowing from the ground into that sphere and it will neutralize it. Okay, is this absolutely clear? So what happens is that the earth, because it's a large store of charge, it can easily give or take the charge from other objects, right? Now it's not always that it will make it neutral. In this kind of situation it does make it neutral, but not always. Okay, so remember that whenever we whenever we connect an object to the ground, to the earth, we call it earthing. That's its symbol, connected with a wire like this. Okay, and that means it can easily give and take charges with to or from the earth. Okay, so remember that word, earthing, and then we can see this alternate method. Okay, all right. Now the method, see here also in the first step what we have is some object that is already charged. Remember, induction cannot be started off with a neutral object. You have to have some object that is already charged. So let's say this is a positively charged glass rod. Okay, and here is a metal sphere or any other object of metal which is once again kept on an insulated stand, right? So what happens is, when we bring this close, so that's what I'm going to do in step 2. Okay, when we bring that object, the metal rod, the glass rod, close to this metal sphere, right? What happens is, like I explained earlier, some of the electrons are going to flow towards this side, towards the left side, and what we have is that the left side of the sphere will become negatively charged and the right side of the sphere becomes positively charged. Right, and now, like I said it earlier, it's like we are showing a lollipop. We are not going to make it touch. So what we do is, in this step, we connect this metal sphere. We connect this metal sphere with an wire and to the earth. So that is now grounded. Don't forget the meaning of this symbol, right? You can see we are grounding this one. Okay, so what does grounding mean? Most of the times it means touching or putting it in contact with the ground by using a metal wire, right? Or you may have noticed, or you may be knowing, that earthing wires in your house go pretty deep inside the ground, right? So even that is a very good level of earthing. For most situations like this where you are charging objects, just touching the ground works very well. Okay, I'm also going to demonstrate what happens when you do that very shortly. So what we have done is, the glass rod is still here, the metal sphere has now been grounded. So I want all of you to think about what's going to happen to these charges, right? Like I said earlier, earth is a big store of charge. It can give or take whatever charges there might be, right? So it is possible that all the charges go away, right? All the positives, all the negatives go away. Do you think that's possible? No, it's not. The fact is that only the positive charges will go away. Only the positive charges will be removed due to earthing. Well, why so? The fact is that when we connect it like this, electrons from the ground will flow up through the wire and they will neutralize. They will make these cations over here, they will make them neutral, right? When the electrons will come from the ground to that point, to the on the sphere, those charges will get neutralized. But these charges, they are not. Okay, now you might say, couldn't these electrons, extra electrons, go into the ground, because earth is after all a big store of charge, it can give and take easily? Well, they don't, because this positive charge holds or attracts the negative over here. So it won't allow these electrons, the extra electrons over here, the negative charge over here, to go into the earth. Okay, so remember again the sentence that unlike charges attract each other. So these positive charges are going to attract these negative, and they don't allow the negative charges to go into the earth, right? So now what we have is, we've got a glass rod which is positive, we've got a metal sphere over here. On the left side of the metal sphere there is negative charge and it is grounded. So what we will do is, now we will remove the ground, that is, we'll leave the glass rod as it was, no change with that. Remember, these two are close, so we'll leave the glass rod as it was, but remove the wire that connects it to the earth, that is, we'll remove the earthing. Okay, So in this step, what we had was the rod was close to it, so negative positive charges were separated. When we connect it with the ground, the positive charges are neutralized due to the electrons coming from the earth, and now we keep the rod right there and we remove this wire. We remove the grounding. Basically, it is connected with something like a switch. This is actually a symbol of switch. Don't worry too much about that. This is a symbol of switch. So when we have the switch in this position, it means the contact is made and charges can flow. So what we'll do is we will disconnect the switch. So what happens now is that charges cannot flow any longer. So this negative charge is still held over here. It did not escape. Like I explained it earlier, the positive charge got neutralized, but the negative charge over here could not be neutralized, or it could not go away because it was being attracted by the positive charge. It is still. And finally, in the fifth step, we remove the rod. Okay, so think about it. When this rod is removed, the attraction on these electrons, the negative charges, will be removed. Alright, so will they go into the earth? No, unfortunately the bridge doesn't work anymore because the bridge has been opened up. Okay, so that means you cannot have these electrons going away into the ground. Correct? So what happens is, when we remove the rod away, when we keep it away from this sphere, what we have is the negative charge of the metal sphere will spread out on this metal sphere, but that charge will not be able to go anywhere. So ultimately what you have is, now that sphere is negatively charged, right? So you can see that's the whole alternate method, right? There are minor differences. In the previous method, you took two uncharged metal spheres and both of them got charged by induction, one positive and one negative. But here we take only one sphere, right? And finally, I hope you see that if we start with a positive object to do induction, the final charge that we have on the sphere is negative. Correct? Okay, so instead of this, suppose we would have started with some object which was negative to begin with, then what would happen is that when we bring this close, the positive charge would stay here on the left and negative on the right. Okay, everything would be reversed. Alright, and finally here you'd get a positive charge on that sphere, not negative. So that's what we have about this method of induction. Again, remember, induce or induction means to act from a distance. Alright, the word induction itself means acting from a distance. So that is what we are seeing in both of these methods. This rod never touches the spheres, but yet it makes them charge, or it gets them charged by this method. Alright, that's why the name is charging by induction. Okay, so that's all really for charging by induction. The next topic now is to determine the properties, or to discuss about the properties of charge. Okay, right, so it's time for that theory, but before we get on with the properties of charge, it's worth winding up all of this by doing one final demonstration, okay, where I am going to show you how to execute this process of charging by induction. Alright, so let's begin with that. Okay, so here I am again, and with my favorite tools. Okay, so I hope you remember that this is called an electroscope. Correct. So now we have this electroscope, right? And I hope you remember that it's a device that is used to detect the charges. It has got two leaves. I really hope you can see the leaves, right? They're made up of aluminum in my case. And I've got this rubber balloon. Okay, what I'm going to do is I'm going to show you how we can get these leaves charged, or this metal wire charged, without the balloon ever touching this one. Okay, so we're going to follow exactly these steps, right? But like I've said, for this method or for charging by induction, the first thing we need is an object that already has a charge. Okay, so that is going to be the balloon. Right now I don't know whether the balloon is neutral or not, but I'm going to charge it by rubbing it against my hair. So I'll do it for a while. I'm confident that very shortly it is going to be charged. Okay, I think we are ready now. Alright, so let's see the steps. Okay, we have the charged object and we have this thing that we want to charge. The first step is to bring them close so charges will get separated, and that's what you are seeing. Okay, that's what you are seeing. Well, why are the leaves going away? Because of the fact that when I bring this close, the charges get separated. So this balloon is positively charged. So when I bring this close, right, the positive charge over here attracts the negative charge on this upper surface, and that means the positive charge of this metal goes to the leaves. Just like here, the positive is over here, so this one becomes or is negative, and the other end, the far end, is positive. So if the balloon is positive, the upper surface over here is negative and the leaves are positive, and because the leaves are both positive, they are going to repel each other. Alright, so here that's what we have. Now we are already in situation 2 in the figure, in the diagram number 2, right? What happens if I ground this object? Now I want to ground this, that's this one. Okay, how can I ground it? Let me show that. See, human body is a good conductor. Okay, human body is a pretty good conductor. So if I will touch this, you can see my feet, sorry you can't, but the fact is I can see that my feet are touching the ground, right? And I'm not wearing shoes. So what that means is that there is a conductor between this point and to the ground, because my feet are touching the ground and human body is a conductor. So whatever charges are developed on this upper surface, they will be neutralized easily by the electrons coming by the ground, right? Because what we have is that when I put this close, so what happens is, because I am grounding it, charges will get neutralized, just like it happens in this diagram 3. Okay, so again the idea is we have got this object charged and bringing it close to this surface, but it's not touching it yet. So the step 3 is that you have to ground it. So I'll do that by tapping my finger. Okay, so see, the moment I tap it, we are already in the situation the diagram 3 shows. Have a look. The diagram 3 shows that there are only 2 kinds of charges now, right? Okay, positive, negative. The balloon is positive, fine, and the negative charge has come to the uppermost surface, and from the leaves the charges have been removed. Okay, so what is going on really is that the leaves have become neutral, right? Okay, so we are going to repeat because I have to explain the process along as I do it over here. So let's start again. So step 1, we have got a charged object and we have got an object that we want to get charged. So the first step is bring it close. Okay, there we are, right? The second step, the third step now is we ground it. Okay, done. Then the next step is I have to leave this balloon over here, right? And I have to remove the ground or remove the earthing. So earthing is by my finger, I'm going to remove it. Okay, done. And the last step is remove this balloon. See, have a look at these 2 leaves, right? They're already quite far away from each other, right? That's, with the little charge on the balloon, it has worked so well, right? You can see that I can tilt this, but in no position will the leaves come close to each other. That's obviously pretty simple, because the leaves are already charged, and that's why they are repelling each other, so they don't want to get close to each other, right? So this is what happens in the 5th step. that the charges want to get away from each other, and that's why they spread on the sphere in the diagram, because the sphere is made up of metal. Here they spread on these two leaves, and that in turn allows the leaves to repel each other, and that's why the leaves get separated. Okay, so now let me do one more thing. If I touch this uppermost surface, what do you think will happen? That's right, the charges will flow into my body and then go to earth. Okay, and the leaves will have no charges remaining. Have a look. The moment I touch it, the leaves fall immediately, right? So that's because the moment I touch it, all the charges go away from the leaves, they go through my body, and then they go to the ground, right? So basically my finger is behaving like this switch. Alright, so let's do this again. I want to show you one more thing. Okay, the other thing that I want to show you about is the fact that if one object is positively charged and you use it to carry out this method of induction, the object that you get charged by this method is actually the opposite, that is, it has negative charge, right? So because this rod was positive, this sphere ultimately gets a negative charge, right? So let's see whether that's true or not. So we're going to repeat the whole procedure, right? So let me rub this balloon on my head. Okay, right, see, it's already allowing the leaves to go away. So what I should do is tap it with my finger first, but don't remove the balloon, and then remove the finger first and then remove the balloon. So you could see they are repelling each other because they are charged. Now what happens if I bring this very balloon close to these leaves, right? Although there is a bottle in between, but plastic really doesn't stop the charges from applying force. Okay, so let's have a look. Do you see that the balloon attracts? Oh, sorry, you won't be able to see that way. Do you see that the balloon attracts the charges? I really hope you can. Have a look here. This is very clear. Okay, so I hope you notice that the balloon is attracting the leaves, right? So that's because of the fact that if the balloon is positively charged and we use it for induction, then this system, this object, the leaves, they have got a negative charge. So when we bring this balloon with positive charge close to the leaves with negative charge, there is an attraction between them. Alright, so again that lends proof to what I've drawn over here, right? That if we use it, if we charge it by this method of induction, right, the charge developed on this sphere and on this rod, they're actually opposite, right? They're different polarities. Okay, so that's it for the demonstration. Now we're going over to the next topic, that is properties of charge. All right, so let's continue with it in a moment. Right, so let's see what properties does charge have. Okay, right, the first one, charge is a scalar quantity. I'm sure you remember what scalars are, having no direction. Okay, so charge is a scalar quantity. All right, second is charge undergoes algebraic sum or addition, right? So what does that mean? Okay, it means that whenever you have a system, let's say a collection of objects, right? Whenever you have a system or a collection of objects, so let's say that in some system there are two objects A and B, let's say, right? And the charge, symbol of charge is generally Q. So charge on A is some 3 units, whatever those units are, and charge on B is -1 units. So that means the total charge on this system is said to be Q total is going to be equal to QA plus QB. You just have to do a simple algebraic addition, right? Okay, so this is ultimately 3 units and -1, that is 2 units. Is that okay? Right? So charge follows algebraic addition or sum, right? See, this is not like temperature. Suppose I'd say that these are two bodies, one has temperature 100 Kelvin and the other has, let's say, temperature 200 Kelvin. What's the temperature of system? And you say 300 Kelvin, right? You shouldn't be here. Okay, so that doesn't work. So temperature cannot be added algebraically, right? You can't just add to get the temperature of the whole system. So remember this property that you can add charges, right, for a system like this, right? So these are two properties. The third one is there is a law of quantization of charge. Now this is very important. Okay, quantization of charge. So what does quantization mean, right? Quantization is a name given to a very basic idea, which is just like what I am going to explain now. See, think of buying Maggi noodles packets, right? Let's say you want to buy one packet, let's say, which is worth 15 rupees these days. The price has shot up enormously, right? Okay, but let's say you want to buy Maggi noodles packets. How many could you buy? You could go to the shop, stand over there, just observe, all right, window shopping, and buy nothing, come back. So you bought 0. Fine. The next day you go back to the same shop, right, and now you could buy, let's say, 1 packet. Fine, valid. The shopkeeper wouldn't be surprised at all. He or she would happily give you 1 packet of Maggi noodles. All right, the next day you go and buy 2, right? You love Maggi noodles, don't you? So you buy 2, right? The next day you're a bit more adventurous and you want to buy 2.5 packets of Maggi noodles, right? So the shopkeeper is just going to stare at you as if you have come from some other planet, right? Because what you're doing is you're violating the basic norms of quantization, right? See, the fact is that some things like packets of Maggi noodles, they can only be traded, they can only be exchanged, they can only be sold, bought or anything in terms of integer number of things. What do I mean? You could buy 0 packets, nobody is going to complain, right? You could buy 1 or 2 or 10 or 100, right? Don't eat that many in a day, right? But if you buy it, if you try to buy it by an amount which is not an integer, there is going to be a problem. For example, 2.5, right? You can't buy 2.5 packets. Okay, you must either buy 2 or 3. That's it. You can't buy 2.5, right? So just like this example of Maggi noodles, there are many things that are quantized as we see around ourselves. For example, coins, currency coins are quantized. You can give 1 rupee coin, all right, okay, then you could give 2 1 rupee coins, you could give 100 1 rupee coins, right? But you can't give 1.5, right? Or you can't give √3 1 rupee coins. So quantization means that you can only have some integer values, right? 1, 2, 3 and so on. So like that, by many experiments, again we have found that if there is any stable particle, in the universe, its charge is always in such steps. Okay, so let me write the law. So the law of quantization of charge says that the charge on any body or object must be an integral multiple of fundamental charge. It must be an integral multiple of fundamental charge. Now what's this fundamental charge? For example, in the Maggi noodles packet case, one packet is fundamental. So you can have one packet or two or three or four, anything like that. Okay, just like that here there is some fundamental charge, right? Okay, that fundamental charge is actually very well known. It is E. E stands for charge of electron, the magnitude of charge of electron actually, right? So what we have is this whole thing can be written in form of this mathematical equation where n is an integer. See, it can be 0, no problem. For example, a neutron has 0 charge, it's neutral, right? Neither positive nor negative. Okay, so neutron has 0 charge, so n can be any integer. It can be 0, it can also be negative, right? In fact, for a proton, this n is going to be 1. Okay, but for, let's say, chloride ion, Cl minus, right? For example, for Cl minus, the value of this n is going to be minus 1. Okay, so quantization of charge says that if you have got any object, any body, then the charge on that object must be an integer multiplied with the fundamental charge, which is E. So that is, it could be 0E, 1E, 2E, 3E, 4E, 100E, 10,000E, integer into E. It could be minus 200E, right? But it can never be 3.14E. Sorry math students, pi not allowed here. It can't be 3.14E. Alright, so this is not allowed because 3.14 is not an integer. So remember, this number n has to be an integer, right? So that is the quantization of charge, right? There are more properties to discover, right? So that's what we'll continue with. Okay, the next property is, remember those superheroes that I talked about, superheroes of physics? Here is one of them. It is law of conservation of charge, right? So charge follows this law of conservation. Okay, so we have already discussed a few conservation laws. One of them is law of conservation of linear momentum, law of conservation of angular momentum, and law of conservation of mechanical energy only if there are conservative forces involved. Okay, so here is law of conservation of charge. The statement of law of conservation of charge is pretty much the same as it is for law of conservation of linear momentum. Okay, so here it is. The net charge, or you could also write, instead of these words, you could write the algebraic sum of charges. Okay, this is what you have to choose between. I'm sure I'll choose this every time. So the net charge, or the algebraic sum of charges in an isolated system. Well, it's a conservation law, it couldn't do without isolated system. So what we have is the net charge, or the algebraic sum of charges in an isolated system remains constant or conserved, right? So that's typical of any conservation law, right? Something should remain constant, and typically again an isolated system. So what this means is, right, let's say that somehow we have made some system, let's say this is our system, and these walls are such that they will make it isolated. Okay, so that is charges cannot flow in or out. So you could say that, you know, here we have very poor conductors of charge, right? Bad conductors, insulators, right? So this system is insulated. Now let's say inside this system there is some body whose charge is plus 1e. You can avoid writing plus, it's okay, you could write 1e. There's another another body inside the system whose charge is 3e or plus 3e, and then there is one more here whose charge is minus 5e, right? Okay, now in this situation, let's say somehow we could observe what's going on inside, right? Somehow we could observe what's going on inside. We have put some kind of detector inside it. So whatever may happen, the net charge, the total of all these charges of the whole system will never change, because all this is isolated. All right, so what this means is, right, any phenomena, any physical phenomena may occur, any chemical phenomena may occur, anything may happen, never ever will the total of the charge change. So for example, right now the total is minus 1e. So I hope you are not afraid of this symbol. This stands for sigma q. You could also write total charge, q total. Okay, so right now you can see that this total charge is, well, plus 1e, plus 3e, and plus minus 5e, correct? Remember the property number 2, that the charges can have algebraic addition, right? So here we are doing algebraic addition. So this total charge is minus 1e. That's never going to change. Okay, that's never going to change, right? So it's possible that these two objects somehow merge with each other, right? What you will have then is one object with one charge plus 1e, and then another larger object with a charge minus 2e. But still, if this is in an isolated system, you can see again that the net charge on the system now is sigma q, which is plus 1e plus minus 2e, which is always going to be minus 1e. That won't change. So anything may happen between these three, right? But because the system is isolated, the total charge will never change. So this, really in a way it means that charge cannot be converted to anything else, right? For example, you have law of conservation of mass. You have studied that in chemistry. We are going to talk about it a bit later in physics, but you have the law of conservation of linear momentum in physics, right? So that says that if some system has got some linear momentum, and if the system is isolated, its linear momentum simply can't change. Anything might happen with that system on the inside, right? Whatever is happening is on the inside, not from the outside, because it's isolated, right? So the total charge will never change, because charge cannot be converted into anything else. Just like linear momentum is one physical quantity on its own, it can't be converted to anything else, right? For example, charge cannot be converted to energy or into mass. Like this won't do. Well, you have minus 5e charge and I have 3e charge. Okay, you have minus 5. Why don't you give me minus 2e? Okay, and I'll convert that to mass, right? And I'll grow in size, and now you have minus 3e charge and I have 3e charge. No, this simply does not work. Okay, charge cannot be converted to anything else, right? So that's the law of conservation of charge. Okay, now that we are done with the properties, I think it's enough to wind up this lecture over here. Okay, so when we have the next lecture, we are going to start talking about quantitative aspects of this chapter, right? We are going to discuss Coulomb's law. We are going to talk about the forces, the values of the forces, right? How much force does proton apply on electron and all that. So well, let's hope we get it soon the next time. Okay, till then, goodbye, see you all.